Okay, so let's welcome Mike Schneider. Mike is joining us from the University of Missouri, where he's an assistant professor of philosophy. Mike is our first in-person foundation seminar speaker. So thanks, Mike, for coming out to Cambridge to give us this talk. And he's one of our, he works on a lot of topics on philosophy of physics, but also works on sort of models of how, of epistemology, if I'm not mistaken, something like that. Okay. But anyway, so Mike is going to tell us why we shouldn't worry about general relativistic black holes and instead love them.
All right, yeah, thanks. So right, I do philosophy, physics, history, and philosophy of cosmology, and I call them social dynamical science. And most of my research is kind of like circling in an orbit of what I take to be the center of all of those, and very few others do. And so it's working out how all these themes can talk to each other. This title is in reference to Kubrick. It's not autobiographical, but yeah, I'll just dive in. So a fetish is an object of inappropriate attribution of value. So what this means is that fetishists have an excessive, which is to say irrational, commitment to that object, given their overall interests. On that definition, the claim that someone is a fetishist just falls out as a criticism. It's a charge or accusation against them. So using those terms, I'm concerned about the accusation that quantum gravity researchers are fetishists, in particular concerning general relativistic black holes. So today is some work in progress figuring out how to refute the criticism. So in a sense, to defend quantum gravity research against this charge of inappropriate attribution of value to general relativistic black holes. And this is part of what I take to be some larger thinking about the general relativistic foundations of the work that gets done on the subject of quantum gravity, specifically quantum gravity phenomenology. So what's going on here in the background is that I'm restricting myself to what you can think of as a fairly austere empiricism, that what science has won for us so far is just some license when we consider our instrumental predicament to talk in terms of modeling applications of our best theories to date. But also an important part of science is the process of scientific advance, how some of our instrumental predicament promotes us to build new theory by means of the current state of the art. I think most conversations about thinking about black holes and quantum gravity research start from a much more realist point of view, that somehow we've learned that there are these objects and now we're trying to get more understanding of those objects. And I am interested in coming at this from, as I say, a more austere angle, that just all we have are the resources that science has gotten us up till now. We're trying to push it further.
What's the general relativistic black hole as opposed to non-relative?
Yeah, so it's going to be dependent on the formal details of general relativity as opposed to those kinds of astrophysical or astronomical events that we have access to. So it's going to be the preoccupation with what you might think of as formal features of how general relativity handles black holes, singularities, event horizons, and so on. So in that light, here's just like the starting social dynamical observation about how the community works. In the corner of research that's preoccupied with fundamental physics of gravitating targets. Well, general relativistic black holes, in this formal sense that I'll say more about, they play a prominent role in quantum gravity research via work on singularity resolution and also better understanding how evaporation through to the endpoint through Hawking radiation goes. Okay, so at first approach, we can imagine just a skeptic peering in on what is going on in quantum gravity research, and they'll wonder why. So why, the skeptic might ask, do these particular formal structures, these mathematical models in the theory of general relativity, why do they get to play such a prominent role?
So are you going to defend the premise that it plays a prominent role more?
Great. No, I'm not.
Okay,
And I'm happy to talk about it
Because-
more later.
it's not my experience that the people working in quantum gravity spend too much time worrying about the formalities of how black holes are defined in GR.
Yeah, so I'm being very intentionally loose here by shifting between the quantum gravity community and the quantum gravity community interested in phenomenology,
Okay,
or phenomenologically motivated projects in quantum gravity. If you look at what's going to count as quantum gravity phenomenology, intense focus on the mathematical features of black holes springs up a lot more, as does Big Bang. I'm being intentionally, so politically equivocating between these two because of that austere empiricism. That somehow when you're starting from that austere empiricism, you're just going to be saying, look, everybody who's not explicitly interested in phenomenology projects is just counting on their friends to be working on the phenomenology while they get it. But we can talk more about that style of reasoning. But yeah, it's political, but I framed it that way. All right, so if the skeptic asks this basic question, what they're after is an intellectual justification for this bit of practice in theoretical physics. And they're interested in it given in the most general terms. So justification would explain the observation about this socio-intellectual trend in terms of intellect, so in terms of reasons and reasonableness, that this is how to proceed in building out new theory out of the current state of the art, consistent with what the sum of empirical evidence to date licenses us to do with the current state of the art. What this means is that the opposite, if we lack this sort of empiricist-friendly justification, the implicit alternative explanation is that the socio-intellectual trend is what you might think of as purely social. This is a case of cultural learning minus good scientific. Think the difference between my picking up prudent good research directives during my graduate training versus my picking up tobacco smoke. A focus on general relativistic black holes is cultural learning minus good scientific learning, and it's a small step to an economic argument of the motivated divisions of intellectual labor within a research community that would entail that the socio-intellectual trend is irrational, hence a display of fetishism on that earlier characterization. In short, the charge of black hole fetishism against the quantum gravity community is the endorsement, at this point, the argument at least, it's the endorsement of the skeptic's worst possible option. That there just isn't an intellectual justification for taking seriously in quantum gravity research the mathematics of black holes as they're treated in general relativity. We all learned it from our advisors like Bad Cigarette Hat. Okay, so in greater elaboration, here's the charge. General relativistic black holes have certain features that are known to raise tricky problems, even paradox. That makes them alluring to theorists looking for productive constraints to shape their task of working out new physics. But ultimately, those physicists dwell too much on these models. The aspects of the models that are responsible for their allure exceed the empirical content of the very theory that makes them salient in the first place, theory that makes them relevant at all to matters of empirical data. It's the part of the model that has nothing to do with why we got talking about it. Okay, against that prosecution, I take it that the standard line begins something like this. Well, we've observed astrophysical black holes, sometimes more directly, sometimes less. And it's that fact about our observation, or our observations altogether, really, that makes them, that makes salient certain models within our current state-of-the-art theory of gravity and spacetime. That current theory's general relativity and general relativistic black holes are the relevant models. Of course, appeals to these sorts of observations aren't going to be alone enough for general relativistic black holes to play a prominent role in quantum gravity research. And the shortest way to see that point is just to note that something analogous is true just about everything we observe in astrophysics. Most of those other space-time models of other astrophysical targets seem to be hardly relevant in quantum gravity research. So the standard line includes an addendum, something like, well, on a physical interpretation of general relativistic black holes, it becomes the case that astrophysical black holes are sites of the breakdown of general relativity. So that new theory is not only needed to underwrite our current descriptions of those particular astrocritical targets, the astrophysical black holes, but rather the new theory is needed to overwrite our current descriptions, to replace, substitute out. So the standard line is a bit of a two-step. Empirical work makes general relativistic models of black holes worth considering within the context of that theory. And then considering them in the context of that theory leads to problems that invite total replacement by new theory. Not just to say,
which problems are you referring to?
so these problems are going to be problems related to singularity to the extent that you take that to be a problem, and paradox or quasi-paradox surrounding black hole evaporation. So once you put it in quantum matter and have to deal with studying the
For quantum
impact
matter,
of
we don't have very good observations. I mean, for quantum gravity, there's not good observations. So if you just take classical relativity, you know whether it is sort of, whether there are so many paradoxes.
Right, so there aren't going to be, if you're just taking classical general relativity, you're not worrying about using classical general relativity to furnish a mean field description of the gravity part of your system. If you're just doing classical GR, the only thing that gets used in the quantum gravity research is this preoccupation with singular structure. That part, at least, is there even in fully classical. But I am in this taking for granted that one of the uses of general relativity is to furnish a background when we start trying to understand quantum matter in various gravitational systems. Okay, so I hope this all echoes as true, because I don't mean to mischaracterize this standard line. I just want to make it as sharp as possible, because the standard line with this addendum raises a question. Why should specifics concerning general relativistic theory about sites of the breakdown of general relativity be expected to help in theorizing general relativity's replacement? So even at the level of logic of theories, that's inherently a puzzling claim. So to have a model of the theory, what's often considered a description of a world in which the theory is true, is sharply to have established that the theory is not, in an important sense, broken in describing just such a world that we're now talking about. And what that means is that we trip a little bit in the two-step that I was describing when we move from considering general relativistic black holes in light of empirical work over to the claim that empirical work has found a site of the breakdown of the only relevant theory supposedly in town. But that's not that logic puzzle is not my concern here. Even imagining that we can formulate some standard of theory breakdown, which is applicable to models of a theory like general relativity, and is therefore sufficient to settle that logical puzzle, we're then going to encounter another puzzle, the second one that I'm interested in. So to focus on this latter puzzle, just suppose that there is some standard of theory breakdown that allows us to declare a broken model of general relativistic gravity. For one standard specific to the case of general relativity, you can check out Jim Weatherall's 2023 PSA Symposium article, where general relativity breaks down. But I'm setting that aside. I'm just taking for granted that we can talk about broken models. If so, here's the second puzzle. Why ever would specifics concerning general relativistic theory about sites of the breakdown of general relativity, specifics concerning broken models of general relativity, why would they be expected to help in theorizing general relativity's replacement? It's one thing, granted, for a breakdown of general relativity to justify work on general relativity's replacement, but surely that just means we're back to the drawing board. Why should detailed study of the broken model provide guidance in building a new replacement? My sense is that the intuition is that the construction of a model is a bit like engineering, albeit maybe conceptual engineering. Consequently, the breakdown, the models being a broken model, is a bit like mechanical failure. And so the study of the breakdown is in some sense like a study of failure analysis, investigating the remains of a catastrophe, say a collapsed bridge, to reconstruct what went wrong, to understand and ultimately do better next time they rebuild. Unfortunately, that analogy is just a stretch too far. Even having supposed that we have worked out a standard of theory breakdown applicable here, it's still the case that nothing literally breaks. It's either a broken model, broken from initial construction, constructed to be broken, however you want to say it, or it's not. So if the addendum to the standard line is that astrophysical black holes are sites of the breakdown of general relativity, now we need an addendum to the addendum in order to make sense of the study of general relativistic black holes as akin to failure analysis, even though this isn't a causal process that has led to something actually getting broken. Okay, addendums to addendums, already getting very cumbersome. It doesn't help the present defense on the standard line that there's another issue, not so unrelated. Maybe this will speak more to your initial question. General relativistic black holes are spacetime models, which we take to represent astrophysical black holes with the help of various idealizations. Meanwhile, we're generally suspicious of the particular idealizations involved, and the suspicion reflects that these are idealizations that specifically involve attributing physicality to global properties of the spacetime, which seem like they cannot even in principle be known to embedded observers about the targets of their observation. These are idealizations about spacetime structure, asymptotic infinity, the locale of the event horizon, and the structure of the singularity hidden beyond them. Now, if the general relativistic description of black holes is on its way to being replaced, and that's why we're talking about them in the first place, we expect to throw away all sorts of claims about black holes where general relativity is misleading. Shouldn't we expect those idealizations that we are suspicious about anyway to be part of what's thrown away? Yet those idealizations are also key to motivating work on singularity resolution as well as evaporation through Hawking radiation, once we consider the use of gravity in the presence of matter fields. So the standard line risks sounding deliberatively inconsistent, that a researcher cannot consistently deliberate about new physics by considering sites of the breakdown of general relativity while they're simultaneously using failure analysis-like techniques to study the broken models. And note that if the standard line is indeed deliberatively inconsistent, then this furnishes a much stronger route to the claim of black hole fetishism. So before I could merely point to a charge of fetishism being a consequence of just taking seriously one possibility raised by the skeptic, now I can say that if the standard line against that possibility of the skeptic is correct, since the standard line involves researchers being deliberatively inconsistent, then those researchers are being irrational. I'll flag here that Dominique Ryder's skeptical charge about a Hawking radiation mechanism for black hole evaporation, which I believe he's presented in this series in the past, it also takes the form of a charge of deliberative inconsistency or deliberative consistency. So I think there's some nice affinity between the prosecution that he ultimately is responding to in his project and this prosecution that I'm ultimately responding to in mine. Eugene Chua's skeptical charge about the role of idealizations, which he's also presented in this series, it's a bit different. Hopefully I'll have time in the end to talk about these. I probably won't, but you can ask me.
Sorry. Yeah, before you go to the response, I'm still a bit confused about what the conflict is supposed to be. So why? So just that first sentence, can you just say again what the problem is?
A researcher cannot consistently deliberate about new physics by considering sites of the breakdown.
So why can't they do both at the same time?
Okay, yeah. So they can't do both at the same time because what it means to have a standard of theory breakdown is just that we're just going to tag this model as a case that we're calling a broken model. In order to use failure analysis-like techniques studying the broken models, you have to think that it wasn't just a unbroken model that's tagged as broken, but in fact that something falls apart and prevents you from having the model. And so the deliberative inconsistency is either we have general relativistic black holes to talk about, or we are committing ourselves to not having those black holes to talk about, and what we're studying is why we fail to have models.
Yeah, maybe this will be sort of in your response, but this seems to sort of slightly bizarre commitments about what it means to talk about black holes, or talk about any phenomena using a theory at all, right? Like it seems to be, it has to exactly match what the theory is telling you, otherwise you're not actually talking about what the theory is telling you, which I think is clearly false.
So let me move forward
Yeah.
because I think this is an issue with the framing of the prosecution, but not ultimately the
Okay.
justification.
Okay.
Good question.
Yeah.
Great. And maybe not understanding what is counted as failure analysis techniques, because I think about updating theories by looking at where they break down and are inconsistent. I guess you could have a mathematical way of thinking this, or you could think about where it doesn't match nature. And I kind of think about Einstein studying Newtonian relativity or motions of various observers, and then being able to do thought experiments to help him motivate special relativity. Was this not a failure analysis? We're looking at where the previous theory fails and using the fact that you need to be able to make your new theory approximate it until the old theory's failure, as well as seeing where it's inconsistent with data. Was that not a failure analysis kind of study that helped motivate finding the update? And is this not the track that people studying general relativity, specifically black holes, are trying to take in their trying to figure out what ingredients might be needed to update to get to a consistent theory of quantum gravity?
Yeah, so one way of responding to this is for me to say, yes, there's going to be a description where that particular episode in Einstein's thinking looks perfectly good, like a failure analysis. The breaking point between that case and this one then becomes what it means to run with it until it actually breaks. In the case of Einstein reasoning about what kind of setting could allow for the relevant phenomena that is approximated by Newtonian but isn't, the part that breaks is still like squarely within the empirical part of the model, whereas the concerns in general relativity become the parts that break are actually nothing to do with the empirical support that leads us to think about it.
Thank you.
All right, so in fact, I don't think the standard line is deliberatively inconsistent, which is why I punted on the pushback of the formulation of the problem. Because I want to fully develop and defend the standard line, which is how I'll attempt to refute the charge of black hole fetishism. So here's my proposal. It'll come in two parts. Start with 3 points of motivation. First, here's an empiricist-friendly way of talking about how future theory gets built out of the current state of the art. Among various different kinds of uses of general relativity in physics, such as setting up GPS, predicting orbits, such as detecting binary mergers, and so on, we moreover use general relativity to furnish empirical leads for research in fundamental physics concerning gravity, especially but not only quantum gravity. To furnish those empirical leads for that work in fundamental physics using general relativity, we consider classes of models of general relativity that are physically relevant. By that, I mean sense of representing concrete physical systems that are targets of interest in that fundamental physics. And specifically whose content is in a restricted regime is known or maybe just strongly thought to be under empirical control with general relativity. Which is just to say, as a general rule of thumb, even if we have possible empirical phenomena that we are interested in, if we don't feel like we have control over them in general relativity, we generally aren't using general relativity to study. Okay, so therefore, along with the observation about research process, here's an observation about phenomenology in the physicist sense of the term. Physically relevant classes of models of general relativity describe possible empirical phenomena in a general relativistic regime of description. Finally, an accompanying third observation about mathematical relativity. Models of general relativity, up to some standard of equivalence relevant, describe different possibilities and that formal differences between two models, that is, features of a model that may vary, represent differently. So models' features are what affect the representational capacities of the model of the theory. So maybe these observations sound peculiar, but I at least hope they don't sound too controversial. Taken all together, they lead to a question. Do all features that may vary of physically relevant classes of models represent possible empirical phenomena in a general relativistic regime the context of doing research in fundamental physics concerning gravity. I punted on your question because this is ultimately the kind of question that my response is sort of engineered to expressly deal with. The first half of the talk was my attempt to build up the charge that would motivate thinking about this sort of question.
So what happened to the quantum here? Is that, I thought that was I guess originally I thought you had classical general relativity, then you have some add-ons that were quantum. And I don't exactly know what those are. Those like Hawking pairs of particles being created near the horizon? Are they full-blown string theory? Are they quantum loop? Are they, is it integrated to protecting the singularity? But where did it go? Where did all that go?
So the short answer, it was narrowly interpreted, not in the first part of the talk. So the setup was meant to be when quantum gravity researchers when phenomenologists are working on black holes, they're taking for granted a lot of the mathematical structure that we get from general relativistic models, classical general relativistic models in the background. So it's why do these classical models get to furnish empirical leads when they go and do that? So right, this was the classical general relativistic foundations of work in quantum gravity phenomenology. It was the part that's supposed to be inserted because of us feeling good about general relativity so far.
The use of models here, you might get into the model theory sense. Or something like that.
Yeah, some classes of models is not quite, but yeah.
Okay, but not in the sort of more colloquial sense of physics where a model is just like some fragment of a theory or something like that.
Yeah, so if you'd like, I'm not quite doing model theory in the logic sense. I'm talking about classes of these mathematical theory classes of models, but it's meant to be closer to the mathematical relativists' treatment of the theory as opposed to the physicists. In language familiar in the foundations of general relativity, we can redo this question. Is every non-ad hoc spacetime property possible empirical phenomena, or representative possible empirical phenomena, a distinct way that a gravitating universe can be empirical? So I claim the answer to that question is no. Moreover, the answer is quite clearly no. Not every non-ad hoc spacetime property represents an empirical phenomenon. Given a model, some spacetime properties of the model outstrip all empirical content, the theory of general relativity and its application to some relevant gravitating target. What the model represents differently from other models that aren't in the same class is not any empirical phenomenon. Here's an example. The most obvious example I can think of is the combination of a property called future extendability and a property of not being causally bizarre. An omega point is a point whose time-like past covers the entire spacetime. And so a spacetime that is not causally bizarre has a trivial set of omega points. Finding future extendability to be fit to purpose is a bit trickier in like slogan form, but a canonical model with property is the bottom half of Minkowski spacetime, where we've just removed everything above t equals 0 and some choice of normal coordinates. The complete Minkowski spacetime, meanwhile, is future inextendable. Both of these models, Minkowski and the bottom half of Minkowski, are not causally bizarre, so this will be our intuition pump. I'd like you to consider it's beyond the capacities of any observer in the bottom half of Minkowski spacetime to observe anything about the fact of future extendability reflected in the model. They may just as well reside in something future inextendable, a complete Minkowski spacetime, given that they necessarily do not reside at a omega point, because the set of omega points is trivial.
Wait, if there were an omega point, then they would be able to tell that it's future extendable.
So the definition of future there gets tricky, but yes, because if you're at an omega point, you can sort of trivially get all facts about spacetime because you can.
I see. I can just sort of look back at everything
Directly
that
into
happened.
it, but,
Clarify one thing, what do you mean by bottom half? Minkowski?
so pick normal coordinates in the origin, extend them globally because we're in the cosmic spacetime, we can do that, and then just delete from the model everything at and above t equals 0.
Oh, I see, okay.
This is just snip it off.
So what's an omega point again? Sorry, I'm not.
Yeah, omega points are points from which the entire space-time is in the time-like past of that point. So there's a future-directed curve from every point in the manifold to the omega. Future-directed time-like.
So there's no like null infinity or anything.
Yeah, exactly. So an example of this would be Minkowski spacetime rolled up. So now that you've snipped it, just perform periodic identifications on your time axis. There's then going to be a future-directed curve from every point to the origin.
So how about you look at the maximum global point? But don't you? That's a more natural notion of space-time sequence. At least
A more natural notion of what?
of space-times you want to look at. I mean, certainly you can cook up anything which has closed time-like curves and all things, which you don't like. I mean, I agree. Right. To prevent such thing, you may naturally look at MGHD.
Yeah, so there are going to be weird situations here. So like generally we like thinking that we can study interior of care, but the maximally global hyperbolic extension of the exterior just gets you to the process. It doesn't get you all the way into where you want to be talking about. I forget where exactly.
I subset the cosherence definition. Yeah.
That would be an unsatisfying way of stating it. But
Well, that's
physically,
okay. That's one of the biggest
Yeah.
objections in the field called cosmic censorship. Sure.
yeah. So this is relevant in the Weatherall paper that I mentioned on standards of theory breakdown. He ends up spotlighting cosmic censorship. In this project, it also ends up showing up playing an interesting role. I don't think I'll have time to actually get that far into it, but I'll come back to that.
But I mean, cosmic censorship, I accept this. Okay, something which is troublesome, but these ones, okay, I think these are trivial. Cosmic censorship.
Yes, so this is meant to be an example just showcasing that there are non-ad hoc properties that exceed the empirical content. So I take the charge that in all the interesting cases, all of these have been thrown away anyway. Yeah. Right, in short, not all non-ad hoc spacetime properties are within the empirical content of the theory of general relativity, at least for an embedded observer. The mathematical theory of relativity. I take the point that this is meant to be demonstrative in a very easy, uncontroversial case if we're just helping ourselves to all non-ad hoc properties we've been talking about.
I mean, isn't a simple example simply that if you have, in our actual universe, there are going to be huge fractions of it that are outside our future light cone. Those are all, right, like because of accelerated expansion, right, kind of just, for embedded observers, huge many properties in the space-time.
So this is where we're going, and I'll walk it back.
All right.
So here's how we clean up our concepts of which sorts of things about these models can we take as empirical content. I'm going to define these terms, but we'll just say space-time properties that are verified or observable exhaust the empirical content in a general relativistic model given an observer. This is the key move of the project. This is like everything else in the remainder of the time is spent developing this, but this is the key to have gotten to in this talk. What I'm suggesting here is a new taxonomy of space-time properties in mathematical relativity, or a new theory of space-time properties in the logician sense. So far I've treated space-time properties as classes or collections of models satisfying a given property. Non-ad hoc space-time properties are when there's some implicit definition of the properties that can be given geometrical significance, and presumably some physical interpretation. How physical? Less clear. These are bread and butter in mathematical relativity for proving theorems that teach us about Lorentzian models, Lorentzian manifolds, and therefore, in the context of a physical interpretation, something teaches us something about gravity, the universe. But mathematicians can also sort these non-ad hoc properties into different types and prove theorems that make references to those types. The most famous example of this is the distinction between local properties and global properties. It's so famous that I think a lot of times, even in physics, we just take as given that there's some intuitive content to this typing. I'm offering another way of taxonomizing. It's a distinction between verified properties relative to an observer, observable properties that are relative to any observer, and properties that are neither observable nor verified. For a given specification of the observer, properties that are neither observable nor verified are then the features of spacetime that exceeds its empirical content in application to some tended gravitating target. And this handles well the maximally global hypothesis. So,
And verified means not verified by an observer.
so proposal at hand for verified, it's observer relative, where the observer schematizes a point in the spacetime model. And that's because to verify a verified property is to find in your past light cone sufficient data to entail that the model as a whole satisfies the property. For instance, the property there exists a teacup in the universe corresponds to a certain teacup-shaped lump in spacetime. This is a global spacetime property. We don't usually think about it in this way, but it falls out of standard definitions of local and global. It's not a local property because it's not true of all members of any covering of that spacetime by open sense. It's a fancy way of saying something very obvious, that in regions far away from here, there's no teacup-shaped lump to be found, so we're not in a plenum of teacups. But it's also a property that can be verified. For any covering of the spacetime whose members are all time-like pasts of points, there's at least one member of that cover that this property is true. Intuitively, verified properties are properties that can be directly established, at least from somewhere. And in fact, they are verified from here. So given an observer, a verified spacetime property is when the observer's time-like past serves as a witness of the spacetime as a whole having that property. I verify the claim that there exists a teacup in this universe when I see the teacup-shaped lump of spacetime within my past light cone. Verified properties of spacetime are the properties that are reducible to facts about the specific region in the universe that's coincident with the observer's time-like past, when we consider that time-like past in its own right. So those are verified properties of, if you'd like, a centered spacetime with a privileged point that we're talking from. Teacup exists in my past light cone, further exists in spacetime at large. Interestingly, and contrary to first appearances, and contrary to what Stark was starting to articulate, the verified properties do not exhaust what we think an observer observes about the spacetime they live in by appeal to their past light cone. Local properties, all of them, are an excellent example of an implicit broader notion about observability at play. Local properties include, for instance, energy conditions and the forms of dynamical laws, since relevant to traditional Lagrangian field theories. Unlike with the verified properties, in order to claim that we observe local properties like forms of fundamental laws, based only on our past light cone, we need to help ourselves to induction. We can think of this as an application of a Copernican principle, which says, so far as concerns the local properties of our universe, the data that our past light cone provides about spacetime is typical. So not only verified properties are observed, but so, in some common use of the term observed, are local properties observed, albeit in this induction-laden way. I'll say that local properties are observable. In a paper that's been in the review process for a while now, I argue for a wider characterization of the observable properties, generalizing from the presumed unproblematic use of the Copernican principle to observe local properties. And the intuitive characterization is that observable properties are those properties of spacetime that are reducible to properties of specific covers of the spacetime, namely covers whose members are all the time-like past points. Because the time-like past of a point is the sort of thing that an observer can possibly verify depending on where they are embedded in the spacetime. So actually observing observable properties requires establishing that my time-like past itself satisfies the property, and then performing an induction not characteristically different from the utterly standard induction that we use in inferring the forms of fundamental laws and energy conditions. So in that paper, I drew some things, the Big Bang property, which is that every time-like geodesic is past incomplete, is observable on this definition.
But this construction, would that preclude some observables?
Observables in the more standard.
The more
sense of-
standard, yeah. What would it preclude? trying to understand, would it preclude something that?
So for one thing, it precludes all teacup properties. So those are not observable.
Those are not-
But it also, I mean, more fundamentally, it includes the location of matter-ized defined by
Yes.
law.
Ah,
This is you know, we read off for the matter-ized.
All the way at infinity, but you're not actually at infinity.
which you will never quite reach, right?
Yeah.
So you
And
get-
also, like, say,
Oh,
final body
right.
mass,
Mhm.
mass of the black hole. This kind of things.
Yeah, asymptotic structure things. I actually think there isn't really time to get this far in the project, but I think it's an open mathematical question whether there are alternate definitions that get us more asymptotic structure than we would think we could get.
Oh, so can you repeat that? So,
I think it's an open maths question whether there are reformulations, weakenings of some of the definitions used for asymptotic structure that get us more
I see.
than
You
we
would-
might expect.
Right.
Yeah. Um,
You'd want that actually, right?
Yeah,
Yeah.
Yeah.
For instance, like intuitively here, we're interested in observable properties. You're interested in properties that are in general can be true of subregions that are in globally hyperbolic settings that are themselves globally hyperbolic regions. And you might hope that additional constructions in highly symmetric spacetimes are similarly reducible to the globally hyperbolic sort of covering spacetime. I sort of jumped the lead there. Global hyperbolicity is also observable. So this is an example, maybe more surprising than a Big Bang property being observable, kind of intuitively. It's very quick to make sense. It's like everywhere you look, you will encounter the incomplete geodesics. But it turns out that causality conditions, at least some of them, not all of them, but I have no reason to think that any of them don't end up counting as observable, particularly global hyperbolicity is observable. Since conjunctions of observable properties are observable properties, we wind up with the upshot that a globally hyperbolic Big Bang is observable. Therefore, the standard model of cosmology involving a globally hyperbolic Big Bang spacetime model of general relativity can furnish an empirical lead of fundamental physics. That's that paper under review. What I've been trying to do today is extend this line of thinking into black holes. And that's the response to this prosecution that I'm trying to launch. If the spacetime properties that are verified or observable exhaust the empirical content of general relativistic spacetime given an observer. In slogan form, everything empirical about spacetime is a matter of luck, cosmic luck in the case of teapot properties, or induction. A source of possible error, but just sort of a generic feature of us doing science. I'll close on this slogan just by previewing the rest of this thinking. There isn't a black hole spacetime property that we can go check whether it's observable or verified. There are instead various features that intuitively characterize what we take to be the theory of general relativistic black holes. And so what this means is we're not going to get a simple line of just, yep, everything we care about a black hole is observable or verified or neither. But what we can do is start, for instance, reinterpreting classic singularity theorems, noting that causality conditions have now been, in some sense, like set on the same plane as energy conditions. We can start to consider weakened characterizations of asymptotic structure that are empirical in the same way that we feel like energy conditions are permissible to account as things that we observe. And through doing that, we can hopefully recover. I think we can recover a decent amount of the motivation for singularity resolution research. I think we can recover as an interpretation of the cosmic censorship hypothesis. We can recover work on semi-classical black hole thermodynamics. We can't quite get evaporation until work out some way of talking about quasi-global mass in an observable, respectable way. So that's the project, and this is the slogan. of the project, this empiricist friendly, this austere empiricist approach to thinking about motivations of using general relativity to study how quantum gravity is supposed to handle things. Thanks.
Okay, we have like 12 minutes for questions. So of course, people on Zoom, you can raise your hands and I can promote you to speak. But other questions in the room? I guess I feel like there was a move at some point from your sort of stylized definition of observable to the more sort of ordinary notion of observable. And I did not find you justifying that move because yes, you can define observable in the way that you did, but then you sort of slip into what is empirical about space-time, and then you sort of rely on your older notion, but I don't know if that's possible. If you want me to say more, I think it's like, it's clear that there's also abduction, right? Not just induction or luck. And I can make inferences about things which I wouldn't, in some ordinary notion, unless you're sort of being positivist about it all, is observable.
So I apologize if I did defend on theoretic predefined notion of observation. I don't think I need to. Depending on how I said things, I might have. Do you accept, for the sake of this conversation, that we have observed the dynamics of gravity?
I mean, yeah.
The dynamics of gravity are characterized by equations at all points in space-time. In order for us to get from actual concrete, even highly stylized, idealized descriptions of our observations of a past light cone to a statement like we even can remotely hope to observe the dynamics of gravity, there's an induction over regions of the model involved. In sort of ordinary language of how science goes,
So
we're going to be doing that by recourse to abduction, but there's an induction going on over as far as the map of the model is concerned.
So maybe I'm a bit confused. So when I accepted that we have observed the dynamics of gravity, I mean, maybe LIGO is like a paradigmatic case where, there were sort of astrophysical black holes colliding and we sort of saw gravitational waves. I feel like that's as good an observation of dynamical gravity as there ever was. Now you're saying that involved some kind of induction over what?
Over, formally in my definition, over the members of a covering of the space-time by the causal past or the chronological past sequence.
So why is that an induction? I mean,
Well, so it's an induction because we're moving from a smaller evidence space to a wider domain, right? We're moving from an evidence space that is one member of that cover, our past light cone, to a claim about every member in that cover. And then it's a feature when we're restricting to observable properties that if that's the case, it's also going to be the case for the space-time at large.
Are you saying like we generalize to saying that gravitational waves are everywhere or?
Yeah.
Okay.
Yeah, so we're happy with the statement that our observations appear to suffice for our purposes. It involves an induction, but that's just like inherent, nature is, we can be wrong. But what we've done is we've gotten verification of the right sort of thing about our past light cone to take for granted that the universal form of gravity in a certain regime has this characteristic form that doesn't depend on its place in the universe. So same thing with energy conditions. There's sort of like weaker quasi-laws or however you want to describe those.
What does
but
it
again,
say about the inferred masses? They're just part of the induction in the LIGO events.
the inferred of the masses of the objects?
Yeah.
So being cagey about the lack of recovering as observable properties a global notion of mass.
Yeah.
I think we have to make I think I have to say the same thing that I would say about the contribution of black holes to the energy budget of space in lambda CDM, which is that we're sort of playing fast and loose with ultra compact objects that might not be black holes, but that we would be comfortable assigning mass and then coarse graining over a region. It feels like more of a structure in the case of LIGO than in the case of energy budget of the large scale structure of the universe, but I think that's what I have it. Unless I can get suitable quasi-global notions of mass that count as observable.
But there is, you can think about some spectrum, some radiation spectrum of giving indication of the masses. It seems like it was a.
I would need to look more close. I suspect that actually ends up in the details looking more like it could just be an ultra compact object that we're assigning a mass in the more usual way to. I need to look at an example and see how it works.
We have a question on Zoom, Helen. Wait, 1 second. Helen, go ahead and unmute yourself and.
Okay, hi Mike. Okay, I think you can hear me. Thanks for the talk. I don't exactly know how to ask this, so apologies if it doesn't really make sense. But the thing I'm wondering about is whether we end up losing information that we could have had from theory. If we broaden our notion of observable in this way that you've said, I worry that now things that our theory would have said, hey, you might have thought that this was observable, or you might have done an induction, but in fact, you should be more worried about these kind of austere cases. We end up, like, how do we make sense of those kinds of claims that we would have gotten from theory if we just say, okay, we're doing induction on whatever we could observe?
So okay. Cool. Maybe the sharpest way of responding to this sort of worry is to just briefly browse through how you can deploy this machinery in the case of the classical singularity theorems. Extendability maximality is not an observable property. Sort of that was the motivating intuition pump earlier on for something that exceeds the empirical content. Spacetime, it's still going to be the case. So what's going on in the interior? Geodesic completeness, even if spacetime is maximal, a kind of conditional statement, is also not going to be empirical content on this sense. And yet, we can formulate a theorem that, in the case of a parent horizon, a marginally trapped surface, given some observable properties about the model in question, it follows that even if maximal, there is at least one incomplete geodesic, future incomplete geodesic in the case of the black hole singularity theorems. Now, apparent horizons are also not observable properties. They're also not verified. By definition, they're going to be a problem for anybody to be exterior. You're not going
But
to.
why are they not observable? I mean, apparent horizon would be so. I mean, you can have the pattern that could.
They're not going to be in my past light cone in the exterior. We're going to have to.
Why do you say the exterior? Why do? I mean,
presumably when we look at Sagittarius A star, we are in the exterior, right? So at the bottom line, the kinds of things that we use to get excited about black holes being a sort of stable, robust part of our current science.
You mean by observations from the Earth? Say,
yeah,
using. Let's say from the fundamental aspect, there's nothing that prevents courageous experimentalists
from diving in. Right. So I think the way to say this is we don't get that the incomplete geodesic at the heart of the black hole, for instance, we don't get that it's observable or verified on the scheme. Like easily provably not. What we do get is that if you think that the formation, the development of a marginally trapped surface is under empirical control by general relativity. Also under empirical control by general relativity is the fact that there's at least an incomplete geodesic. So this isn't a major this is just a reskinning of the singularity theorem, but hopefully it is actually capturing why all along that kind of result was seen as so gratifying or so satisfying for motivating then work on singularity resolution. So to get Helen's
So what, this has some bearing on the interpretation of the EHT image as light skirting the horizon, right?
so yeah, pull apart. There's an astronomical event, which is a verified teacup property.
Yeah.
It is of interest if such things are of interest as quantum gravity corrections on photon ring. It is not of interest to quantum gravity in the way that motivates singularity resolution
I
without
see, okay.
committing to saying that the formation of marginally trapped surfaces is itself under control of the theory.
So do you want to quickly respond to Helen? You were in the middle
Well,
of your
but hopefully, yeah.
No, it's okay, it's okay.
What I was just going to say
Carried away.
to Helen's question here, hopefully this illustrates how the austerity of what is going to count as verified or observed doesn't, or I don't think ultimately limits how we deploy theory in the context of building future physics. I think it clarifies what kinds of theorems that we can derive in general relativity are serviceable in that project.
Bishop, do you have?
Okay,
You have like 1 minute if you.
Going, gone.
I can ask one other question, but so if you restrict yourself to like observers on the exterior of say black holes, then but already that notion of what is an exterior is then not even observable. Because again, the exterior is separated by the event horizon, which itself is physiologically defined. But
Yeah, so the very quick answer is I was slippery in this talk, but I did mention that technically the definition of verified is with regards to centered spacetimes, where we just have declared a point. I'm taking it as for granted, although the pushback is fair enough, we might be inside a black hole, for instance, that the centered spacetimes that we take to be the physically relevant ones when we're doing science typically are ones in which we're centered outside if the privileged point just happens, as a matter of fact, to fall outside the relevant nominal astronomical event that we're observing.
So that's the luck part.
Yes, that's the
Right, yeah.
cosmic hook, contingent, ultimate contingent.
Okay, I think we are at time, so thanks, Mike, and Columbium is downstairs in half an hour.
Interesting.